Greetings everyone. Welcome back into Calc 2. Here's a quick little section on some alternate ways to approach an integral. And it's basically based off of the years and years and years of people building up formulas and ideas of integrals. There, in pretty much every calculus book is included a table of integrals, which has anywhere from 100 to 200 formulas on some basic integral structures that can be manipulated to help you through quite a few complicated integrals. Also, modern technology has a lot of good software that knows how to integrate both generically and numerically. I want to talk about both of those methods with just two examples in this lecture here. So, integrating by formulas, which are the tables, and by computers, which they're called computer algebra systems. When I do the computer algebra system skit in between these two scenes, I'll be using GeoGebra, that's what I like to use a lot. And then I'll also demonstrate Wolfram Alpha, which is a very popular intelligence engine. Okay. In your OpenStax textbook, Appendix A lists an entire table of at least 110 different integral formulas. It may even be more. It's over 100, I know that. Obviously, the numbers I'm using here. Okay, and here's an example integral. It looks pretty straightforward. It's just a square root and a little bit of an x in the denominator, but it actually is a lot more complicated than it seems. And it involves a couple of different methods if you want to employ it by parts or some trig subs or, just stuff all over the place with these things. And it's quite a few daunting, steps in making sure you're keeping your algebra straight. However, in the past, someone has already laid out some formulas for just these kinds of basic structures. And all you need to do is look in the table of integrals and find the integral format that fits your structure, at least closely. It doesn't have to be right on, but within a manipulation or a substitution. Okay? Now this one doesn't require a substitution. The next scene I'll do one that requires a substitution. So notice I'm looking at the format where I have the square root with a binomial, and the binomial is linear. Okay, that's important because there are also binomials that have quadratics in them, differences of squares and things like that. And that's exactly what I have here, a square root with a binomial. And you see du is my variable, it's linear. And then I also have a u to the 1 in the denominator. And that's just exactly like this structure. And that was formula number 109 in the table. Okay, so then what it tells me is, here's how you format your answer. All right, equals 2 times the square root of the same binomial plus a times the integral of 1 over u times the square root of that binomial du. Well, then that begs for another formula, right? In fact, the one right above it in the table, number 108, is exactly that integral. And the reason why they list it like that instead of putting this in there is because this particular integral had two different answers, and the answer that I have written here is specifically for when a is greater than 0. And if you'll notice, a is the number portion in the binomial, and our a is exactly greater than 0. It's 3. So that's why I picked this particular solution. There are actually two answers for this formula in there, and I picked this one because of the selection of a. So I'm going to put these two formulas to work to give myself an answer to this integral. Alrighty, so here's my structure, but I'm noticing that I have a 2 here instead of just the u. So I'll start by pulling the 1/2 out. I have a square root of 3 minus 5x over x dx. And they're using u while I'm using x, no big deal, right? Okay, so now I've got my 1/2 is going to be multiplied by everything. So I'm going to start here. That's going to be 2 over 2, because the 2 from the formula and the 1/2 that I'm multiplying in. Square root of 3 minus 5x, because it's the same binomial in the formula, plus a, which is 3, times. Okay, now right here, I'm putting times, okay? And it's telling me to do this integral. Instead of rewriting the integral, I'm just going to jump straight in since I've got a formula for that. 1 over square root of a, and notice a and b are the same setup. That's handy. So 1 over square root of a is going to be 1 over square root of 3. Oh yeah, and don't forget, it's times a half. So that was why I wrote this little before. I reminded myself now. It was times the half, so that this 1/2 is getting distributed in both places here. Okay, and then I have ln, absolute value, square root 3 minus 5x minus the square root of 3, because it's the square root of a there. I'll close my absolute value, put my plus c here, and then my denominator is the square root of 3 minus 5x plus the square root of 3. Okay, so then the only simplifications that I can see to do would be, of course, to reduce this 2 over 2, which 2 over 2 is just 1, right? So it's just there. And then right here, you could actually rationalize this, this fraction right here as 3 over 2 times square root of 3 over 3. If I multiply the square root of 3 up there. So then this would reduce to just square root of 3 over 2 times the logarithm there. So as you can see, this would not have been necessarily a very straightforward, simplistic antiderivative. It would have required many steps with some of the advanced integration techniques, especially to go from the square root to something with the logarithm in it requiring this particular setup. Okay? So I hope that you see how I've picked these formulas on purpose, but you would have to actually go search the table for that. Now, go take a look at what this would look like in the computer algebra systems. So let's take a look at the formula tables first I was showing you. This is in the OpenStax textbook. And as you can see, these are the two formulas that we just used for the integral that we were just doing on the board there. You can see number 108 and 109 there. And as you can see, there are lots and lots of these different types of integrals of all different kinds and formats for all different occasions. They have all the inverse trigs, and they have hyperbolics and exponentials and logs, and a lot of different combinations of trigonometric integrals. You should take a look at these integrals, and they're actually contained in most college calculus textbooks. Okay, so computer algebra systems. Here is Wolfram Alpha, and what I'm going to do is I'm going to type in a command, which there's no specific commands here. The computer intelligence system does its best to translate what it thinks you want. I'm just used to doing these certain commands from the different math programming languages that we've done, but don't necessarily have to be these things. But if you type int, you see it gives you a list of things that it could interpret, right? So most of them for int is integrate. And once you put a parentheses like this, inside of the parentheses it's waiting for something to integrate. So next I'm going to type square root, SQRT, and put a parentheses. And then I have 3 minus 5x. Then I want to divide, and I'm going to open another parentheses, 2x. And the reason I need the parentheses there is so that it counts that all as one denominator.
Then you're going to want to indicate somewhere in here that x is your variable. Most of the time with these commands, it's just a comma and then another x. This is actually a very similar format structure that you would use in most graphing calculators as well when they have a computer integrating system. Okay, so I'm going to hit enter now, and we're going to see what it comes up with. So there's a first solution for us right there, and you'll notice it involves this inverse tan with an h. That's an inverse hyperbolic tangent. Notice it's still thinking, and here it goes. It plugs out a few more. Here's the one that we'd be more familiar with right here. This particular solution just has the logarithm split up, and notice logx, it tells you right here, is the natural logarithm. This particular system just likes to have its logarithm structured in a certain way and separately, and you can see even the radicals are formatted somewhat differently than what we were doing. That doesn't mean that the answer is incorrect or that ours is incorrect. It's just a different algebraic setup, and you can see it's very, very similar. They have the square root of 3 over 2 in front of each one, and it has the radical plus something and minus something in there. So it is actually the same answer, it's just their interpretation of it. Now here's GeoGebra. For GeoGebra, what we do is we type in the function first. So I have y equals, and then I'm going to do square root of 3 minus 5x, and then I'm going to divide by 2x in parentheses, just like before. And the cool thing here is that we get the graph right away of the function that we're looking at. And now I'm going to integrate it. So in GeoGebra, once you start typing, it tries to find the command for you. And the one we're interested in here is this integral one right here, because we just want to do a generic integral of the function and tell it what the variable is. So I'm going to hit that. Notice our function name has already been given to us. It's f right here up at the top. So I'm going to just type f at the bottom, and for the variable, of course, I'm just going to hit x. From here, I just hit enter. And you'll notice that what it's actually done is it's tried to give us a graph. But remember, there should be a plus c after it. And GeoGebra has interpreted that as giving us some other constant to add right here. You'll notice that if I shift this, it does actually change the function over there. And that's because it's allowing me to take a look at different plus c values. It does recognize that there's supposed to be a plus c here. It's just not giving a generic one. It's actually trying to give us specific ones. But all that really does is shift the answer up and down. Okay, so notice here, this is actually a lot like what our format looked like, right? It looks a lot more similar to the integral that we were using before, as far as the radical structure and things like that. But it is still the same thing that we were doing. And by the way, the upside to using the computer algebra systems also is that the integrals that you want to actually plug in values for, the definite integrals, like let's say I want to do the integral of this thing from -5 to -1. I could actually do that in this command here, function f, and -5 to -1. And the cool thing about GeoGebra is, do you see how it's actually shaded in the region for me right here? You can see that it's showing me, and it also has given me the decimal approximation of that area without having to do anything else. You could do the same thing in Wolfram, by the way. Up here in my command, after the x, you could just put comma -5 comma -1, and it should actually give a very similar answer. See, and there it is right there. It's giving -3.10892. And if you remember, GeoGebra just had the -3.11. It just rounded to the 2 decimals. I think that's just because GeoGebra is set for 2 decimal float. You can actually change that to where GeoGebra will show more decimals. But you can see it's the same answer, and you can see they actually gave a decent little semi-subgraph here comparative to the GeoGebra one here.
For the other example in this lecture, I want to show you one that requires a substitution. So I want to do the integral of 7 over x to the 11th times the inverse sine of 1 over x to the 5th dx. Seems pretty complicated, right? And, you know, it's no slouch. So what I did was I searched through the list, and I found an integral of u times the inverse sine of u. And that doesn't seem to fit, does it? Because I have something in a denominator, and it's more like x to the 11. But I noticed this. It's just u, and then this is the same u, right? So right here, what you need to see is that I actually already have a fraction here too. And this is sort of the same format, right? Okay, so what I've actually got here is something that can hold up to a u substitution. Okay? So then this is what I'm going to do. I am going to let my u equal to 1 over x to the 5th, right? Which is x to the negative 5 power. So then my du is going to be the derivative of this, which would be negative 5x to the negative 6 dx. So let's rewrite that a little bit. That means my du would be negative 5 over x to the 6th times dx. Okay, so I just need to do a little bit of manipulating of the pieces here. And here's what I'm going to do. I'm going to rewrite this as negative 7/5 integral of 1 over x to the 5th inverse sine of 1 over x to the 5th times negative 5 over x to the 6th dx. Now bear with me here. Look at what I've done. I took the 7 out front, right? I multiplied and divided by negative 5 at the same time, and that was to accommodate my substitution. So you see the negative 5 consequence is here, and the negative 5 that I need for the substitution is there. I multiplied and divide by it. The x to the 11th, I split into a 1 over x to the 5th and something over x to the 6th. Because 1 over x to the 5th is going to be my u, and the negative 5 over x to the 6th is part of my du. So notice what I have now gotten is negative 7 over 5 integral u times inverse sine of u du, which is exactly what I have the formula for here. Okay, so then the answer to this is this, right? Since I used u, it's a direct substitution. I can just take this, and that is physically the next step that you would see. So now I'm here. I'm exactly in this spot for my antiderivative. Okay, so then what I'm going to do is I'm going to start writing the correct answer with x, because this is my next step. That you could physically take this and put it here as the next step. Although I've already got it written, so there's no point. My u from the integral, all right, I'm going to have my antiderivative here. U is 1 over x to the 5th. Don't forget the negative 7/5, right? So I have negative 7/5 times 2, u is 1 over x to the 5th. So 1 over x to the 5th minus 1 over 4. Inverse sine of 1 over x to the 5th, because that's what u is, right? Plus, now of course that negative 7/5, right, is on all of this. So I've got negative 7/5 times u is 1 over x to the 5th square root of 1 minus 1 over x to the 5th squared, and then that whole thing is over 4 and plus c. Okay? Now, of course, depending on your application, this could be a perfectly fine way to leave your answer. But let's simplify it just a little bit, because that's going to make it look a lot more like most of the things you'd see in the computer system also. So let's just clean it up a little bit. To clean up this fraction here, all I'm going to do is multiply. Whoops, I forgot something, guys. I hope you caught it. There's a squared here. Yeah. I'm going to notice that the x to the 5th squared is actually x to the 10th, but it's 1 over it. So if I multiply times x to the 10 times x to the 10 times x to the 10 on both the top and the bottom of this fraction, it will actually wipe out this x to the 10 portion. Okay? And then the next thing that I'm going to want to simplify is this radical right here. Okay? So to simplify that radical right there, I'm going to notice that this is the same thing as the square root of 1 minus 1 over x to the 10. Right? Because that's what the squared and the x to the 5th is. But instead of 1 right here, I will instead put x to the 10 over x to the 10. Okay? And the whole thing is in the square root, by the way. That looks a little sloppy, but when I simplify this, I'm going to have the square root of x to the 10 minus 1 over square root of x to the 10. And this piece right here, the square root of x to the 10, I know you're tempted to say, oh, that's just x to the 5th because it's 10 divided by 2. You're mostly correct, okay? But this is actually going to be square root of x to the 10 minus 1 over the absolute value of x to the 5th. And the only time that that's going to matter, of course, is when x is a negative number. We didn't actually plug in any values on our integral here, okay? But if we had positive values for a definite integral, then you wouldn't even need to worry about the absolute value. But we didn't pick any values. X can be negative here, although it be kind of iffy, goofy, whatever. But it can happen. So let's write out the simplified version here. I have negative 7 times 2 minus x to the 10. Which, of course, the negative you could multiply in and get x to the 10 minus 2 if you wanted to. It doesn't really matter. And in the denominator, I'm going to have 20x to the 10 times the inverse sine of 1 over x to the 5th. Minus, right, because of this, I'm going to have 7 times the square root of x to the 10 minus 1. Right, that's from that radical being simplified there, over the 5 times the 4 here is going to give me a 20. This x to the 5th, right, this is 1 over, the x to the 5th can come to the denominator. And from the radical, also times the absolute value of x to the 5th. Okay? Now, plus c. Okay, so in a second, I'm going to show you also the computer algebra system version of this integral as well, just so that you can see another example of using computers to do these kinds of integrals. Don't forget that just because the answer looks a little bit different doesn't mean it's wrong. Some of these integrals have multiple versions and multiple different ways that you can go, depending on if you want to use hyperbolic trig functions, which some of you may or may not have talked about yet, I know. And other times they may want to go with logarithms, or there's all kinds of connections between all of the different trigonometry functions, with identities and things like that. Connections from inverse sine to inverse cosine and inverse tangent and all of that stuff. So there's other ways of simplifying these things. These formulas were just one particular path and one major route that just gets used a lot. Okay? But sometimes when you plug these into the computer algebra systems, they may look a little different. and that doesn't mean they're wrong. Okay, a lot of times computer algebra systems are really good to check if you're doing the definite integrals. Okay, so I hope this lecture has shown you exactly how you can use a table of integral formulas, and also a little intro to make you interested in wanting to learn a little bit of how to get into a computer algebra system to take a look at some of these advanced integrals.
Okay, so for this one, here's the formula that I used from the Appendix A of the OpenStax textbook. As you can see, it's exactly like the one I wrote on the board. Let's go with Wolfram alpha first. So if I'm going to integrate that, I'm going to type integrate, right? And then I've got seven over x to the 11. Notice I use the little caret marker, which is above the 6, times, and I'm going to do arc sine like this. It's much easier to type in arc sine than it is sine with a -1, so that it doesn't get confused with an exponent. So I'm going to type arc sine, and it's 1 over x to the 5th here. So that was the integral that we wanted to do. And I'm going to put comma x for our variable. So there you can see that this one tends to give a very, very similar answer to the one that we were using on the board there. And then of course it also tries to give the other alternates for this one. You can see the connection with the other inverse trig functions there. And then sometimes it'll even try to expand it in other ways, and you get these other advanced mathematical techniques with expanded polynomials and things like that. But the one that really hits this one's really close to what we had and what we are interested in. Okay, so let's try GeoGebra. In GeoGebra, I will have y equals 7 over x to the 11 times arc sine of 1 over x to the 5. And there's our function. So now let's do an integral of that function with that variable. And here you can see GeoGebra has a much different structure, but you see a lot of the familiar pieces like the square root with the x to the 10 minus 1 and things like that. But notice it's switched over with a little bit of inverse tangent mixed with a little bit of inverse sine. And it's like I was saying before, there's a lot of different algebraic and trigonometric connections with these identities and things like that. That doesn't mean that either one of these is wrong. It just means that they went a different route with their particular generic solution.